Welcome back to Very Ordinary Differential Equations. In this lecture, we begin our study of linear first-order systems of equations. Well, what is a system of equations? Suppose y1 through yn are all functions of t. A linear first-order system of equations is given by the collection y1 prime is a sum of functions of t times yi. So a11 y1, a12 y2, all the way up to a1n yn, plus a forcing function f1 of t. Also, y2 prime can be written as a similar sum with different coefficients and another forcing function, all the way until yn prime is its own linear differential equation in y1 through yn plus its own forcing function. So with n different functions y1 through yn, we have n different linear first-order differential equations here. The aij are functions, not necessarily constants, by the way. Now, if every fi is 0, in other words, if all the forcing functions are 0, it's called a homogeneous system. Okay? It's not enough for some of them to be 0. In order to call this a homogeneous system, you need every one of these forcing functions to be 0. Notice that the yi primes can depend on the y1 through yn, but not their derivatives and not second derivatives, etc. Okay, so we have a linear first order system here. Now, any linear differential equation, here is a nice standard nth order differential equation, can be rewritten as a first-order system. This may sound surprising that an order n differential equation can be interpreted as a first-order system. Well, let's let z1 be y. So I'm going to define a bunch of functions, and z1 is simply the function y. z2 is y prime, all the way up to zn is the n minus first derivative of y. So the original differential equation then, the nth derivative is just the first derivative of zn. So zn prime plus p1 times, well, hey, the n minus first derivative of y is what I defined to be zn. The n minus second derivative of y was zn minus 1, and so forth, all the way down until y itself was just z1. So the original equation can now be written in terms of my z1 through zn, and the only derivative that appeared was right here. So overall, note now that z1 prime, well, z1 was y, so z1 prime is y prime, which is z2. z2 prime would be y double prime, which is z3, and so forth. So z1 prime is z2, z2 prime is z3, all the way up to zn minus 1 prime is zn. But zn prime, from this equation here, is f of t minus all of these terms here. So z1 prime is expressed in terms of the z's. It's a very simple expression, it's just z2. z2 prime is expressed in terms of the z's. And so is zn prime. It's expressed in terms of all the z's plus possibly a forcing function. Now, for first-order linear systems of equations, there's a very convenient way to represent them with matrices. So suppose you have the following first-order linear system of equations, same notation that we had a few slides ago. Define each of the following. Take your coefficient functions a11 through ann and turn them into an n by n matrix. Take your functions y1 through yn and turn them into an n by 1 column. Take your forcing functions f1 through fn and turn them into an n by 1 column. Then the original system is just y prime. The derivative of this column would just be a derivative of each term, y1 prime, y2 prime through yn prime. The product ay, well, this is n by n, this is n by 1, so the result is n by 1. So what would be the first entry? It would be a11 y1, a12 y2, a13 y3, all the way up to a1n yn, which is exactly what we have here in our first equation. And then the forcing column just adds on that first coordinate to give you your f1. So row by row, you can verify that a, y plus f exactly gives you the right-hand side here. And the left is just a column of derivatives. That's just y prime. So our first order linear system of equations with this matrix notation has been greatly condensed and is easier to write. Now for a single linear first order homogeneous equation, y prime plus something times y is equal to 0, we would solve this by separating variables and get y prime over y equals negative p of t. But suppose you have a homogeneous linear first order system, y prime equals ay. You can't try to do the same thing, and I've seen students try to do it, because y is a column vector. You cannot divide by vectors. You can only divide by non-zero scalars. Okay, so y prime equals ay we can't say is some kind of separable equation. We're not going to solve it in that manner. All right, so let's suppose we have this general system, y prime equals ay plus f, where A is an n by n matrix. All of the entries of A are continuous on the same interval I. Then the set of solutions on I is n-dimensional, and any linearly independent set of n different column vectors y which solve the system forms a fundamental set of solutions. So we have an n by n matrix here. If I can find n linearly independent columns that solve it, we're going to call that a fundamental set of solutions, and any arbitrary solution would be a linear combination of this fundamental set of solutions. And if you are given y of a for some point in the interval, that's now an initial value problem. Here we have a first order differential equation with y as a column vector being your function. If you are given the value of that column at some point inside the interval where everything is continuous, then there is in fact a unique solution. So this matches our typical way of approaching initial value problems. If we have a first order differential equation and we know the value of the function at a point, there is a unique solution. So let's suppose you happen to know n different column functions, y1 through yn, which solve our differential equation y prime equals ay plus f on the interval I, and this is an interval on which every entry of the matrix A is continuous. Then y1 through yn form a fundamental set of solutions if and only if they are linearly independent. How do we check for linear independence? If and only if the n by n matrix formed by taking each of those columns and making them the columns of the matrix has non-zero determinant at every point in the interval I. This matrix is called the Wronskian of the vectors. However, checking for this determinant to be non-zero at every point is a lot of work. What turns out to be true, and this very well matches our earlier work for higher order equations, if and only if the determinant is non-zero at a single point in I. For our first example, let's represent this equation as a first-order linear system. Well, we write z1 is equal to y, z2 is y prime, z3 is y double prime, z4 is y triple prime. We haven't gone all the way up to the fourth derivative of y because that is going to be z4 prime. So here we get z4 prime minus 2t times z4 plus the sine of t times z3. There was no appearance of y prime in here, so then we just jump right to minus z1, and on the right, e to the minus t. So z4 prime can be solved for in terms of all of the other z1 through z4 plus a forcing function. Therefore, we can just use this matrix and this column for z with a forcing function that only has a single entry. So just check. In the first row, I would get 0, z1, a single z2. And what would I have on the left? I would have z prime. z1 prime equals z2. Indeed, it does. In the next row, I would get 0, z1, 0, z2, z3. But this is in the second row, so that corresponds to z2 prime. z2 prime is z3. Yes, it is. The only thing left to check really is the last one. Negative z1, 0, z2, negative sine t, z3, plus 2t, z4, plus e to the minus t. That is exactly z4 prime. So we have these right here, and now you just go through and check that yes, indeed, z prime, a column of derivatives, is this square matrix times this column plus this column. You'll end up with exactly z1 prime is z2, z2 prime is z3, Z3 prime is Z4, Z4 prime is this expression right there. For our second example, suppose we have 3 tanks filled with liquid. They have volumes 200, 150 liters respectively, and fluid flows back and forth between them according to this diagram right here. So pure water flows into tank 1 at a rate of 10 liters per minute. Tank 1 actually drains 18 liters per minute into tank 3, which sends 3 liters into tank 2. Tank 2 sends 8 liters back into tank 1. However, tank 2 has also got 5 liters per minute of a 4% salt solution flowing in. And in order to make this all balance out, we need to drain 15 liters per minute out of tank 3. So you can check, each tank has as much flowing into it as out. 10 and 8 in, 18 out. 3 and 5 in, 8 out, 18 in, 18 out. So everything's nice and balanced. Let's write a first-order linear system of equations in matrix form which represents the concentration of salt in each tank at time t. We're not going to attempt to solve this system, we're just going to write the differential equation that represents what's going on here. So let's let y1, y2, and y3 be the concentrations of tank 1, tank 2, and tank 3 at time t. Now, since their volumes are 200, 150 respectively, if they have concentration y1, y2, y3, then the amount of salt is 200 y1, 100 y2, and 50 y3 respectively. The reason I'm talking about amounts versus concentrations is that it's easier to discuss the change in the amount of salt rather than the change in the concentration of salt. Let's take a look at tank 1, for example. What is happening to the amount of salt in tank 1? It gains nothing from the pure water flowing in. That is changing the concentration, but it is not affecting how much salt there is. Okay? So the amount of salt in the tank is not being changed by pure water being added in. However, 8 liters at a concentration of Y2 is flowing in. So how much salt is that? 8Y2 amounts of salt are flowing in from tank 2. But I am losing 18 liters at concentration Y1 because it is flowing out of tank 1. So minus 18Y1 amount of salt is from the outflow that goes into the third tank. So altogether, 200Y1 is the amount of salt in tank 1. The amount of salt is changing by gaining 8Y2 and losing 18Y1s. Now let's take a look at tank 2. Tank 2 has this inflow here, 5 liters per minute at 4% solution. That's 0.2 units of salt flowing in per minute. It's also getting 3 liters at whatever the concentration of tank 3 is, that's 3Y3, but it is losing 8 liters of its own liquid, so minus 8 liters at concentration Y2. So altogether, how is the amount of salt in tank 2 changing? The amount of salt in tank 2, 100Y2, changing, prime, is given by negative 8Y2 units flowing out, 3Y3 flowing in, and 0.2 units flowing in from this external solution. Finally, how does the amount of salt in tank 3 change? It is gaining 18 liters at concentration Y1 from tank 1. It is losing 3 units at concentration Y3 by flowing into tank 2, but it is also losing 15 units at concentration Y3 by draining out. So altogether, the amount of salt in tank 3, 50Y3 prime, is given by 18Y1 flowing in minus the 18Y3 flowing out. So what 3 equations do we have? 200Y1 prime is 8Y2 minus 18Y1. 100Y2 prime is minus 8Y2 plus 3Y3 plus 0.2. And 50Y3 prime is 18Y1 minus 18Y3. From this point forward, just to recover some space on the page, we're going to get rid of that diagram up above. We've got our fundamental, equations that we're going to work with. The diagram is no longer helping us. Okay, so here were the 3 equations that we had. Solving for y1 in the first equation, solving for y2 in the second, and solving for y3 in the third. And you may wonder why I've bothered to include some zero terms, because I want all of them to match something y1, something y2, something y3 forcing function. Something y1, something y2, something y3 forcing function. Something y1, something y2, something y3 forcing function. Now here were our three equations. We can represent it in matrix form like this. Notice on the left we have a column of derivatives, that's y prime. Then we have negative 18 over 200 y1, 8 over 200 y2, 0 y3. That simplifies to negative 0.09, 0.04, 0. 0 minus 8 over 100, 3 over 100. 0 minus 0.08, 0.03. This is just what's multiplying each of the yi's. 18 over 50, 0. Minus 18 over 50, 0.36, 0. Minus 0.36. What forcing functions are being added on? 0, 0.002, and 0. So we have a matrix form for our mixing tank problem. For our third example, let's verify that the given functions y1, y2, and y3 do solve the differential equation y prime equals this matrix times y. Well, we're going to just go term by term. In the top row, on the left, we would just have y1 prime. That's easy to compute as negative 12 e to the 6t. Now, what would be the top row on the right? It would be 3y1 plus y2 minus y3. 3y1 plus y2 minus y3. y1, I substitute 2 minus 2e to the 6t. I substitute y2 and y3 as well. So 3y1 plus y2 minus y3 is all given here, which does indeed simplify down to negative 12e to the 6t. So in the first row, y1 prime really is equal to all of this. So the top row did indeed check out. It's what this matrix would have spit out for the top row on the right, and it matches y1 prime. Similarly, y2 prime can be computed according to the middle row of the matrix, and everything simplifies as it should. y2 prime really does match 3y1 plus 5y2 plus y3. Similarly, y3 prime does match negative 6y1 plus 2y2 plus 4y3. So each row checked out. Indeed, on the left, y1 prime, y2 prime, y3 prime as a column was equal to that matrix times the column y1, y2, y3. So the given functions do solve the differential equation. Well, altogether, what did we discuss? Systems of differential equations provide a new, more general way to talk about differential equations. First-order linear systems can represent complicated scenarios of interdependent phenomena where y1 depends on y2 and y3 and so forth. And there's a very natural way to present them with matrices. Higher-order systems of one function can even be represented as a first-order linear system, and we saw an example of this. So if we can determine how to solve first-order linear systems, we are actually also simultaneously talking about solving linear higher order equations of a single function. Checking whether a given set of functions solves a linear first order system is a little more tedious than in the single equation situation, but ultimately it was just a matter of computation, checking that everything works. What we haven't discussed is how to find solutions to linear first order systems of equations, but that is coming up shortly.